Okay, again, what is the virtual displacement, right? The virtual displacement which we call it this dW, some from dr, sorry. What's this? This is simply a displacement, but it's infinitesimal. It's a very small one. Arbitrary. It can be any value. Okay, it's infinitesimally small. It has to be admissible. What do you mean by admissible? It has to be allowed. It has to be allowed by the constraint. We agreed from the beginning that we have to respect the constraint. Admissible meaning allowed by the constraint, which means, so for this mass, I cannot say my dr equals dx in the I direction and dy in the j direction. No, because dx is not allowed. I can say my dr equals dy in the j direction. That's perfectly fine. Okay. The same here. You cannot say your dr2 equals dx in the other direction and dy in the j direction. No, dy is not allowed. Okay? So it has to be respected by the constraint. This is what you mean by admissible. So it's not a big deal. Typically it's the case. Typically it's the case, but you have to have it in the back of your head. And if you simply get the work done by the forces through this virtual displacement, this is what we call dW. It's not directly with respect to time, it's virtual work. Okay? Through the virtual displacement. And at equilibrium, the sum of all these virtual work using applied forces is simply zero. This helps us to solve the problem of equilibrium. Straightforward. And if you compare here here are the two solutions, right? So here you need to have this. Why we're always saying that analytical mechanics, we're simply turning a crank. We don't pay too much attention to the details. Here you need to pay attention to the details, the errors of the forces, take care of all the forces. Over there is just working with the scalars. Okay, we're turning the crank. Actually, this is very programmable. You can program this procedure. This is quite hard to program. So any computational mechanics problem, what do you call it? You call it computational mechanics? Any multi-body dynamics, the programs of multi-body dynamics, they use analytical mechanics for sure. Okay, they construct Lagrangian and write down equations with respect to Lagrangian, like we're going to see. Any question? Yes, Mohammed?
I believe all of these R's should be written in the same frame, right? Same coordinates.
R's?
Yes.
Not necessarily. They are not related to each other. All what I did with this R is to dot it with F2. So in this regard, in order to carry this operation, these two have to be in the same frame. And these two have to be in the same frame. But the scalar you get from here is irrelevant. You got it from what frame? You can work here in some frame, here in another frame. Whatever you like.
So if we have several masses, several frames, complicated to put all of them in one frame, we can work with them separately. Like
Oh yeah.
everything in its own.
The scalar product, the dot product is independent on the frame that you work in. Let's relate this guy to another important principle. You guys mostly familiar with it. Any question, please? We just warming up, okay? So still Vaping mechanics, as we're only working with equilibrium, statics, no dynamics, but we're getting there. Yes, Ken?
So for that question, for F1 and F2, we need to list all the forces exerting on the mass.
You need to what?
We need to have all the forces that.
All the applied forces acting on each mass, yes. ignore the constraint forces.
Even though the M2J is in the y direction.
It will, yeah, so this is good. Thank you. This is a good question. Why should account for for this guy here, right? That's the question. Yeah, if you're clever enough at this thing, okay, you know immediately from the beginning that this guy is perpendicular to your motion, just ignore it. But if you work from first principles, this has to be there, and your procedure will automatically cancel it because you're gonna dot it with 0, okay? And this leads to us to actually a good thing. Let's see. What does this mean? Geometrically, what is the geometrical meaning of the principle of virtual world? We're saying that this quantity is 0. What is this quantity? At equilibrium, no motion, in order to achieve equilibrium, this equation has to be satisfied. What does this equation represent? This is a dot product between what and what? Between the applied load and the admissible motion, the directions of your motion. Okay? So what they have to be with respect to each other? The applied load has to be what with respect to the admissible motion? Has to be what? Perpendicular. So to achieve equilibrium, your applied load has to be perpendicular to the motion. Makes sense. Otherwise it will move, right? Otherwise it will move. So many of the simple problems you can simply solve them with this concept only. Okay, you need this force to create an equilibrium. Okay, I'll just make this force to be perpendicular to the allowed motion. And this gives you an equation, and that's it. Okay? So we have this guy, equation here. Most of the time, we will work this course at least with forces coming from scalar potential. So your each F is simply negative partial V partial Ri. Okay? Potential energy. If you substitute each F over there dotted with dRi, what do we get from the principle of virtual world? What do we get? So this guy is partial V partial Ri. Summation or partial V partial R1 times dR1, partial V partial R2 times dR2, partial V partial R3 times dR3. This is what?
0.
Yeah, this equals 0, but this is what? This is dV, right? So what's dV? If V is functions of the positions, if V is function of R1, R2 up to Rn and Rn. What's dV? It's partial V partial R1, dR1, partial V partial R2, dR2, and so on, right? So if Fy is this guy, if we substitute over there, we immediately get that the principle of virtual work reads as follows. dV equals 0. So the potential energy at equilibrium doesn't change. Its first derivative is 0. This is the principle of minimum potential energy. At equilibrium, your potential energy attains its minimum. Okay? At equilibrium, your potential energy has a 0 slope. Differentiated with respect to any of your Q's, you get 0 at equilibrium. Okay? Let's consider this problem. This is example 2.2 Mirovich. There is a spring here. There is a rod over there. And this rod has some mass, M. This angle is theta. We're giving K of the spring, M of the mass, length of the rod, and we're asking about the theta for equilibrium. What is theta for equilibrium? Any question, please? Any question about the description of the problem? You see it? Please, if you have any question, just stop me. Okay? So let's at least sketch the solution using Newtonian mechanics. Well, using Newtonian mechanics, I will have here this guy. There is mg down. What else? What other forces acting
L
here?
connecting.
What is it?
T.
Yeah, okay. And what else? Normal force. Otherwise, I mean, these two forces only cannot be in balance, right? Normal force maybe in x, and this is the theta. Where is the theta with the horizontal here? Okay? I can write down two equations. T is unknown, nx is unknown. Okay? Over there, the same thing. What equations do we have? Forces do we have?
Restoring force.
We have negative kx of the spring here, right?
Restoring
Displacement, and what else?
gravity.
We have T. So you can now appreciate very much this problem or the last problem. You can appreciate very much Newton's third law. Because if the third law is not there, these will be two different unknowns. This would be a problem. And we will not have closure, actually. We cannot solve this. So at any rate, this is T, negative x, kx. What else? And the normal force as well. Some other normal force, ny. And theta is unknown in this case, okay? So, if you write down the equations there, let's write down the equations. What do we have? In the x direction, we have t cosine theta minus kx equals 0. X is related to theta. We're going to see that in a minute because of the geometry. The other equation is ny minus t sine theta 0. These are two equations. How many unknowns, please?
Kx, T, and theta.
X is related to theta. We're going to see that in a minute. So we have t, theta, and ny. You cannot solve, right? We have to also come here, unlike the last problem. So write down the two equations, please. What do we have? We have nx minus t cosine theta 0 and t sine theta minus mg is 0. So get your t from here, substitute it there, solve two equations or whatever, or the first equation to get the theta. Okay? We still need to do more work, right? But I'll just postpone it to the analytical mechanics. You see how much work we did here, right? Let's do it over there. I can do it using the principle of virtual work, fine. But actually, since all the forces are conservative here or coming from a scalar potential, I only have, what forces do I have? Remember, we ignore constraint forces. So what are the acting forces in all this problem? I do not need to isolate things.
FMG.
It's exactly mg and the spring, right? The spring has its own potential and this guy has its own potential. Let's please write it. So here is my potential. It's simply for this guy is negative mg times the vertical distance. This vertical distance is L sine theta, correct? Plus 1/2 k x squared. What is this x? The problem says when the spring is unstretched, the link is in the horizontal position. This guy, so we have here x naught up to some point, and then x from here. Whereas, what is this distance now? Do you know? He's saying when the spring is unstretched, so just x naught here, this guy is horizontal. So this is actually L, correct? You see what I'm saying? So what is x? Or some exaggeration. What is x now?
L by L minus
L minus L cosine theta. So this is, we need to do this anyway for either way of solving it, right? Okay, so this is my potential. Instead of doing all this work, I have just a punchline. What's the punchline? My potential energy is minimum. Its derivative with respect to any q is 0. In particular, the only q here, the only little q here is theta. So dv by d theta is 0. This is your only equation. Punchline, get your unknown. So please differentiate this with respect to theta. This is negative mg L cosine theta plus k L squared 1 minus cosine theta times sine theta. This is 0, we're done. This is a single equation in single unknown, which is theta at equilibrium. Solve it. So we have tan theta 1 minus cosine theta equals mg over kf. Okay? Any question, please? Any question? Yes, Michael?
It was, well, my question is about the theory that you have been explaining about the principle of minimum potential energy. Could you explain it again? Can you explain it again?
Explain it again. Okay, no, sure. Do you mean the derivation? Where, how I got it?
This.
Okay. This guy will give in this relation now. I'm saying that if all your forces come from scalar potential, okay? So you have this equation already, you know it. I'm gonna just substitute this guy in here. So this is partial V, partial R, I. Negative. Okay? So you have partial V, partial R, I, the DRI, sum over the i's. You get simply dV. This now is dV. G work is negative dV.
This means that
Yeah, we already know this from before. We previously derived that change in, or the work done is negative the change in potential energy, right? If you